Good evening, all. Welcome to DSA with Python session, day 7. So, in today's session, we will discuss about linked list data structure. So, let us start the session. Yeah, am I audible? Yes, am I audible? Okay. So, in this session, we will discuss about the linked list data structure. So, what is linked list? Linked list is a linear collection of data elements. It is a linear collection of the data is organized in a linear fashion. Okay, termed as nodes, and each element in the linked list is called as a node. The data is organized in the form of nodes that are randomly stored in memory. This is another important point to be noted. Okay, so these nodes are randomly stored in the memory, unlike arrays. Okay, whereas in arrays the elements are stored contiguously, meaning contiguously means one after the other. Okay, so there is first element, there is second element, there is third element, there is fourth element. Okay, so this order is maintained in array. This is called contiguous memory allocation. Whereas in a linked list the nodes are stored randomly. Okay, that means they are not stored contiguously, continuously, one after the other. Okay, so one node is stored at some place at some memory address, second node is stored at some memory address, then third node is stored at some other address. Okay, so these nodes are connected in a linear fashion by using pointers here. Okay, so then this becomes the next node. Like this, the sequential order. Okay, so the linear order is given with the help of pointers in the linked list. So the linear order is specified using the pointers. Okay, so even though they are not stored contiguously one after the other, okay, but logically speaking, they are in linear order. Okay, so that linear order will give to the linked list by using pointers. So this is simple example how the elements are stored in the form of a linked list. Okay, so here this is called as a node. Okay, so we call each of this as a node. Okay, this is node, this is also a node, this is also a node. All these are called nodes. Okay, so in the node there are two parts. One is called the data part, where we'll store the actual data, and the second part is called the next point. Okay, so this is a pointer which points to the next node in the linked list. Okay, so this is a pointer which points to the next node in the linked list. Pointer points to the next node in the linked list. So this is how the linear order is obtained with the help of these pointers. Okay, so that means along with the data we also store a pointer. Okay, so these two combined into single entity, that is called as a node. We call it as a node. Okay, now you can see here this node address, the node D, element D address is present here. Okay, so this node address is present here. Then this node address B address is present here. Okay, then what about this first node address that is present in a pointer called as a head? The first node address is always stored in a pointer. We call it as a head pointer or start pointer. You can give a name like head or start. So this way if you organize the elements, okay, so such a logical organization of data, okay, so is called a linked list. Now they are organized in linear fashion. See, first element, then comes the second element, this, okay, then comes the next element, then comes the next element. Okay, so that means the data is organized in a linear fashion. So in simple words, a linked list consists of nodes where each node contains a data field and a reference. Okay, so that means a link, it contains a link or a pointer. Okay, so we call that pointer as a next pointer, which points to the next node in the linked list. This pointer always points to the next node. The meaning is the next node address will be stored here. Okay, so it contains the address. Next node address will present here. Okay, so this next node address will present here. So address will store in a pointer. Okay, so that's why it is a pointer. Then why we require this linked list? Okay, so what are the disadvantage with arrays? Already we studied arrays. Okay, so if you see the disadvantage with arrays, then we can understand the advantages of a linked list. Assume that I have a variable called as stack prices storing numbers. Okay, so which represents the prices of a stock. Okay, so these are the stock prices, and this is how the values are stored in the array called as a stock prices. These are their addresses. Okay, so these are addresses here. These are addresses here. Okay, so first element 298 is stored at address 500. Okay, so next element 305 is stored at 504 address. Okay, so next element 320 is stored at 508 address. That means these are integer numbers, no? So each integer occupying 4 bytes of data in this. Okay, so now if this is the initial organization or storing of elements in the array, okay, now we want to insert an element 284 at location 1. Okay, so location 1 means where it is index 0, this is index 1, this is index 2, this is index 3, and this is index 4. Okay, so this 284 we want to add at index 1. Okay, that means after 298 the next element should be 284, then the next element should be 305. That way we want to insert this new element. Okay, so then what we need to do, we'll write like this. Okay, so stock prices dot insert 1 comma 284. Okay, so in Python we know that these arrays are a dynamic list. Okay, sorry, uh, lists are arrays will implement in the form of a list here. Okay, so these lists are nothing but dynamic arrays in Python. Okay, so even though they are dynamic, but there are some disadvantages that we need to understand. So what we'll do then, this statement, when you write this statement by using the insert function, okay, so it inserts 284 at location 1. Okay, so then the new array looks like this, 284 inserted. Okay, then you can ask what is the problems are already with single statement using this insert function, already it is inserted, no? Okay, so then why we need to worry about these arrays? Okay, so internally what happens that we need to understand. Okay, so if you understand the internal organization or internally how this is done, okay, so then you can understand the problem with the arrays. Okay, right? So what it does, how it has inserted this 284 after 298. Okay, so that means it moves all the elements to the right by one position starting at 305. Okay, so that means first the 392 will be moved to the next location, then 301 will be moved to this location. Okay, so then 320 will be moved to this location, then 305 will be moved to this location. Okay, so then the element 284 will be inserted at this location. Okay, so after inserting this, now this is the memory diagram of the new array, stock prices array. Okay, this is how it looks like. Okay, so you may ask what is the problem? Some internally it is taking care of, no? Okay, so why we need to worry about this? Okay, so here the complexity, if you see the complexity of inserting an element into the array, that means almost it is traversing, moving almost n number of, approximately n number of elements, one position to the right. That means it is traversing all the n element once. Okay, so that's why for inserting one element, the complexity becomes order of n, order of n. Okay, so how it is done internally that we need to understand. For example, when you create an empty list like this, stack prices. Okay, so what Python will do is Python creates an empty list. Okay, so it creates an empty list. Okay, then it allocates some capacity for that list. Okay, so initially it allocates some capacity like this. Say for example, some 5 elements. This is not visible to the user. This is not visible to the user. Okay, so internally Python interpreter will do this. Okay, so initially with the initial capacity of 5 elements will be allocated for this array called as a stock prices. Okay, now this is implemented in Python. It is implemented in the form of a list. No, so list is a dynamic array. Dynamic array in the sense that means the size can be increased or the size can be decreased. Okay, so that means the array can expand or the array can shrink. That is called dynamic array. Okay, right. Now, if you add 3 elements, okay, so how we can add? By using the append function, stock prices dot append 298, stock prices dot append 305, 320. Then the 3 elements will be stored in this list like this. Okay, then if you say insert 1 comma 284, now you have 3 elements, you want to insert 284 at a location 1 or at index 1. Okay, so 284 we want to insert. Now this becomes index 0, this becomes index 1, index 2, index 3 and index 4. So here we want to insert the new element 284. When you execute this statement, okay, so insert function, when you execute, what happens? It moves 320 to the next location, then it moves 305 to the next location. Okay, so that means this 320 comes here, then this 305, comes here, then this 284 will be inserted. Okay, so here 284 will be inserted. This is how internally the Python organizes or inserts this new data. Okay, now see, it is creating, first it swaps values to make a space for 284. Okay, so it is just swapping the values, you can see here. Okay, so 320 coming to the next location, 305 coming to the next location, then the space is created for 284. Okay, so that means two copy operations it is performing. Okay, so for one element to insert, two copy operations it is performing. Okay, how many elements are there in the array? For three elements. Okay, so for three elements it is performing two copy operations. Okay, yes or no? Because it needs to copy 320 from this location to this location and 305 from here to here. Two times it is performing copy operations. Okay, so if there are 1 million elements in the array, assume that our array contains 1 million elements. Okay, so now we have to do 1 million swap operations. 1 million times you need to swap the elements. You can assume how much time it consumes. Okay, so that is the problem. Even though all these are hidden from the user, okay, but internally it takes time. That's why your program becomes slow. So once the space is created, then it will insert 284 at a location 1. Okay, so at index 1 it stores this 284. This is how the new array looks like. Okay, so that is one problem. Okay, so if the size of the array is larger, then the number of swap operations also more. That is one problem. Okay, so let us look at one more problem. For example, your array is full. Assume that initial capacity, it internally it has allocated a 5. Okay, just assume that. Okay, you created an empty list here, stock prices, then you added a 5 elements into the list. Okay, so then the 5 elements capacity will be full. The array now becomes a full. Okay, so that means initially the array populated 5 elements populated into the array like this. Now you want to insert new element 284. There is no extra space provided for this. This is the initial capacity 5. Now a new element you want to add into this. Okay, so now how our dynamic array, okay, it will be added. It is not visible to the user. Okay, so 284 will be added moving these elements, but internally how it gets extra memory for this new element, that we need to understand. Okay, so even though it is a dynamic array, the list is dynamic array, internally how it works, that we need to understand. Now if you see the space before this 298, this is the space available here. Okay, after 292 this is the space available. Okay, so but if you consider that, okay, so these memory locations are allocated to different program, okay, or some other variables in the same program are using this memory. Okay, so it is already used, this space is already used, you cannot use for this. Other variables are using this, you cannot overwrite this space. If you overwrite, what happens? Those variables data will be changed. Okay, so then your program malfunctions. Got it? Okay, so this is used space and this is also used space. Then you want to add a new element 284 into this array. Okay, so it cannot use these locations since they are occupied here. Okay, so this is already occupied and this space is already occupied. Then what the Python interpreter does? Okay, so then how to add a new element? Will it give error or will it add? Okay, so when you execute this insert function, definitely it adds new element at location 1. It adds 284 at location 1. Okay, but how it performs this internally? Okay, so Now if you see, it moves some different area of memory. Okay, so what it does is it goes to a some different area where more availability of memory is there. Okay, so inside the RAM, then it tries to get extra space, allocates more capacity, and copies these elements one by one. All these elements from this memory it takes out and copies to a new memory where enough memory space is available. Okay, so this is how our dynamic array works internally. Diagrammatically, if you want to see, for example, this is something like some address. Okay, so at some address 2004 onwards, okay, so it has occupied this memory. So then what it does is it checks where uh, consecutive memory for 10 to 15 elements is available, free space is available. Okay, so then it finds that memory, that means, for example, if this is something like the first element 2004, then this becomes a 2008, then this address becomes a 2012, this address becomes a 2016, this becomes a 2020. Okay, so only 5 elements can be stored here. Okay, so but you want a new element to be added, so what it does is it finds a new space, free available space. It checks where 10 to 15 elements where I can add. Okay, so assume that the space is available at address something like 1000. Okay, so then this becomes a 1004, then this becomes a 1008. Okay, so like this it gets a extra space. Okay, for these 5 elements. Okay, plus what it does is, because you are going to add new elements and it assumes that you want more space. Okay, so then what it does is it tries to allocate an extra space which is double the capacity of initial value. Okay, so it acquires additional capacity which is double the initial capacity. Okay, so this 5 capacity plus extra 10 total for storing the 15 elements, because immediately it should not get uh, a problem with your program. If you add more elements, then you should not get stuck with those elements. Okay, so that's why it acquires more space it acquires. And now what is it does is, from this memory location from 2004 2008, one by one it copies into the address 1000. Okay, so this element copies into, sorry, this element, okay, it copies into this space 305. Okay, so this element it copies to this location. Okay, this element, like this. Now all the 5 elements, 5 copy operations it performs. Okay, so then at location 1 a new space is created and that new element will be added, 284 will be added at this new memory location. Now if you perform one more insert operation, now you have enough space here. Just you can see here, you have enough extra space available after, because the array elements should be, or the list elements should be stored contiguously. Yes or no? Contiguously they must be stored. So that's why it acquires this extra space and now runs your program. Okay, so what it is doing? It is trying to find extra space and it is performing copy operations. This is the problem. Okay, so with arrays. Okay, even though the lists are dynamic, okay, but internally the dynamic arrays works this way. Okay, so this makes your program slow. So generally when it acquires an additional space, okay, so it is double the capacity of initial space. This is called doubling the array. Okay, so here what is the overhead? The overhead is not only swapping the elements, it is not only swapping these elements from this to this new location. Okay, then allocating new memory location and copying elements from old memory to new memory. Okay, so this is the old memory, then finding the new memory, allocating new memory here and copying from old memory to new memory, all the elements copying is the overhead which slows down your program. Okay, so that is why this is not the efficient method. Okay, so using arrays when you have large data, using arrays is not considered to be efficient. Okay, just for inserting one element, you can assume how much uh, work it is doing internally. Okay, the overhead on the program. So to overcome these problems, okay, so we arrange the data. Okay, so we have a data structure like this. Assume that we have a data structure like this where the individual values are stored in a different memory locations. In previous, it is stored contiguously. The elements are stored contiguously. Okay, getting contiguous memory is also difficult sometimes. Okay, so you need a chunk of memory, free memory you should get. Okay, so sometimes getting chunk of memory, free memory is also difficult. Okay, so instead of that, if you store elements at different locations and connect them in linear fashion, then it becomes a efficient organization. Okay, so that is called a linked list. Okay, so now what happens? Array stores values in contiguous memory location, whereas this linked list data structure stores element in a random memory location. You can see here the first element address is 500, next element address is A1, next element address is C5, D7. Okay, it is enough to just acquire this 4 plus 4, 8 bytes of memory if it is available at one place. That's enough. You can store one element. For integer 4 bytes, for pointer 4 bytes. Okay, so 4 plus 4, 8 bytes at any place if you have just 8 bytes of memory. But whereas here in previous slide, okay, so 5 plus 10, 15, 15 for the 60 bytes free space at a time. Okay, so you should get a chunk of 60 bytes of free space should be available. Then only you can copy these elements. Okay, otherwise you won't insert this element into the array. That is the problem. Okay, so we call this kind of organization, this data structure is called as a linked list. Got it? Now, so what we are talking in the linked list, the advantage. Okay, so if you organize this way, the elements. Okay, so you can ask what is the advantage, sir? They are also seems to be one after the other. Okay, so here we have drawn them in linear fashion. But if you consider, you should look at these addresses. They are not one after the other. Just we have drawn for our convenience. The first node address is 500. Second node address is A1. It is somewhere else. It is C5. It is somewhere else. All are at different location. We connected them in linear order, in linear fashion. Okay, by using the pointers. That means the second node address, see here, that we have stored here. That means it is pointing to next node. See here, C5 address we have stored here. It is pointing to this element. Like this, we store those nodes addresses and we'll get this linear order with the help of pointers. Okay, so logically we have organized them in linear fashion, but physically they are not linear. Okay, now you can ask what is the advantage, sir? Okay, so when you want to insert a new element 284, okay, so here no need to move any elements. No need to move elements towards right, to the right. Okay, no need to perform copy operations, copying elements from one location to another location. Okay, so it's very easy. Okay, so it is just modifying links or pointers. Just by modifying the two pointers, you can add new element into the list. Okay, so you can see here how easily you can add a new element. You can just allocate 8 bytes of memory for the new element, 8 bytes of memory you allocate, and you store 284 in that memory location. Okay, so once you store 284, then if this is to be the second element, okay, then 298 becomes the first element. Okay, so the next pointer here, previously a1 address is there. Now what we do is we'll store this node address here. So this node address is something like 702. Now if we store 702, nothing but we can say that this pointer is pointing to 284 element. Okay, if this is the second element, now previously it is pointing to 305, now we made it to point to 284. Okay, so if this is the second element, then 305 should become the third element. That means in the next field of this element in this node, okay, we'll store this address here. So that means the pointer here is pointing to this. Now you can see here 298. When you go to next, you come here 284. When you go to next, you go to 305. If you go to next, you go to 320. Next means you go to 305. Next means 292. Okay, since there are no more elements, the last element next pointer contains a null value. Now see, we haven't disturbed any element nor copied any element from one location to another location. Just we created a new node here, inserted this element, added this element into that new node, then changed two pointers. Okay, one pointer here and another pointer here. Okay, so that is the advantage of inserting elements into the linked list. Okay, so even though in Python arrays are implemented as lists, okay, but we have seen the disadvantage of these lists. Okay, so internal working principle of these lists we have seen, and which makes our program slow. Okay, so organizing the data in this form. Okay, so this data structure is called as a linked list. When you have huge data to manage, okay, so better to use this linked list. Now this is the way in which the new element is added into this. So we do not have copied the values from one location to another location. Okay, so insertion operation becomes extremely easy in this data structure. Adding new element is very easy in this. Now that means if you observe this, okay, so inserting element at the beginning, okay, so takes a constant time, which is represented as order of a one time complexity. Okay, so if you want to add an element at the beginning, okay, so directly you can add, just change pointers here. Then deleting element at the beginning also takes order of one constant time. Okay, so order of one time complexity, because the first element only we delete. Okay, but whereas insert deleting element at the end, if you want to add new element at the end, somewhere here after this, okay, so you need to traverse the entire list. Here it takes that means almost n elements you need to traverse. If there are n elements in the list, linked list, you need to traverse n elements. Okay, so insert and delete operations at the end takes order of n, or in the middle also, because roughly we need to traverse the list, no? So the insert and deletion is order of n. Okay, but the overhead of moving elements from one memory location to another location, okay, so that is removed. That is not there. So advantages, what are the advantages? No need to pre-allocate the memory space. Okay, so inserting and deleting element is very easy. Okay, so traversal is complexity is order of n, you can see, and accessing element by value is also order of n time complexity. Now if you see the advantages and disadvantages compared to Python lists. Okay, so linked list and Python list. because we are implementing linked list in Python, no, using Python language. So since Python already has a data structure called list data structure, okay, so compared to list data structure, what is the advantage of our linked list, that we need to understand. Okay, first in terms of storage, generally the Python list occupies contiguous memory locations, okay, but whereas the linked list will be stored at different locations, that is called scattered memory locations. Then size means it is dynamic, okay, but resizing can be slow. Even though the lists are dynamic, but when the list is already full, resizing becomes slow here, okay. But here linked list is dynamically growing or shrinks down dynamically, okay, so which is very easy. Then random access, it is efficient if you want to access any element at some location. In Python list, it is efficient. It takes order of one constant time. Okay, but here it is inefficient. Traversing random access is, that means you need to traverse search the elements order of n time complexity requires the traversal. Then inserting and deletion here. Okay, so it is inefficient in order of 1 n complexity, okay, that means it requires shifting of elements. But whereas here constant time complexity, if you want to add at the beginning, somewhere in the middle or end, order of n time complexity. So memory means less memory overhead, okay, but here more, that means directly will store only elements here, no extra thing will store here. So okay, so that's why from memory point of view it takes less amount of memory, but linked list takes more memory compared to Python list. Why? Because due to pointers, along with the number we are also storing the pointer or element extra, we are storing pointer in the each node, which consumes extra 4 bytes of memory. Okay, so that's why the memory requirement will be more compared to Python lists. Okay, so these linked lists occupies more memory compared to arrays, or you can say Python lists. These are the some of the advantages and disadvantages. So where we use these linked lists in the real world, okay, practical implementations, applications, if you see, they can be used to implement queues and stacks as well as graphs and trees. Okay, even trees, graphs and trees can be implemented using the linked list. Okay, so they are useful for much complex tasks like cycle management in the operating system applications. Okay, so there we use a linked list. So now let us implement the linked list in Python. Okay, so how this linked list can be implemented? We'll slowly create the linked list. We'll start with empty linked list, and element by element we will add into the linked list. Okay, so how the code should be written for such a creation of a linked list in Python. Okay, right? So let us implement this. Now, what are the things present in this linked list? Each element is implemented in the form of a node. Yes or no? Okay, so how your node looks like? Your node looks like this. This is a node. Okay, so here we'll store some data and a pointer. Okay, so this is data field and this is a pointer, and we call this pointer as a next pointer. Okay, so two different things. This node, okay, so you need to implement as an object. Everything in Python, okay, so you should implement as an object. Okay, so to create a node object, we must define a class for this node. Yes or no? Okay, so first what we do is we'll create a class called as a node. Okay, so that you can create objects. Each object becomes one node here. Okay, so I am defining a class. So it is always better write the code on piece of paper. Okay, so each line of code you should hand code. Okay, you should write on your own. So first to implement the node we define a class here. Okay, so that's why in previous session we discussed about classes and object. Okay, so if you have missed that video, so please go back to the video and watch that video, how to create a class in Python, how to create object in the Python, how to define a class. All such things are discussed in previous video. Okay, so class node will define class node. Okay, so then what we need to do, whenever a node is created, okay, so it should be created automatically. Okay, so automatically means the constructor must be called. Okay, so what is the name of the constructor in Python? It is init method. Okay, so we will define the init method here. So define underscore underscore init, which creates the node. Automatically the node is created. Okay, so then as I said, the first parameter should be self. Okay, so which is a reference to the current object. Okay, then the second one, what we required, a data. Okay, so that data will come to this, so that data we required. Okay, so these are the two arguments we required here. Okay, so what we need to do, that means when this init function is executed, it creates the node like this. It creates the node like this. So then what we do, we'll say that self dot data. So that means this data, there is an element called as a variable called as a data class variable. Okay, so self dot data is equals to data. Now you say, then the next pointer we want to assign, so it creates this variable and assigns this value. Okay, so then it creates the variable called as next, and then say, so since it is the first node, always what we do is we'll store a none in the next pointer. Okay, so instead of a null in Python, we call it as a none here. Okay, so self dot next is equal to none, will say. So this is the class for creating a node object. Okay, so then we want to create a linked list. Okay, so for that also we need to define one more class here. Okay, so I define the class. Okay, so called as a linked list class. Linked list, and every class definition should end with a colon here. Okay, so class name followed by colon. Okay, then so here also what we need to do, we need to create a pointer, head pointer, yes or no. Okay, so for example, if this is your linked list initially, like this node address is present here. Okay, so the first node address we always want in the pointer called as a head pointer. Okay, so that's why in this class what we required a pointer variable called as a head, and whenever we create an object, this entire thing will implement as an object here. Okay, so this is called a linked list object. This entire thing we implement as a object. Okay, so that's why we are defining the class for this. Got it? So that means when you create the object, automatically this head pointer should be initialized. So initially what it contains, just it creates the head pointer. Since you haven't created any linked list, okay, it should create a variable called head, and initially it should store none here. Okay, so for that what we do is we define a constructor here. Okay, so underscore underscore init underscore underscore. Okay, the first argument is always self. Okay, so then any extra thing required here? No, because the variable has to be initialized. No, so it is self. That's it. Okay, so then you define a initialize the head pointer here, self dot head is equals to, then you say none. So when you say self dot head is equal to none, this is how the head pointer is created, because initially our linked list is empty. Got it? Okay, so then what we need to do, we need to add elements one by one into the linked list. Okay, so for that, for each of these we define functions for this. Okay, so you can see if this is your linked list like this. Okay, if this is your linked list, you can add element at the beginning of the linked list, you can add element somewhere in the middle or at some position, or you can add the element at the end of the linked list. These are different possibilities for adding an element into the linked list. Okay, so for each of these options we should define a function. Okay, so first I'm defining a function to add an element at the beginning of the linked list. That means the new element must be inserted as a first element. Okay, so for that we define a function called as a, okay, so insert at beginning. Okay, just you define a function called as a insert at beginning. So for this, what we required? We required the parameters called as self, and also this data you should pass. If you pass this data, the data will be inserted at the beginning of the list. Okay. So what you need to do, how the new element, new node to be inserted. For example, initially, okay, so this is your linked list. Assume you want to add a data value is something like 10. New element 10 has to be inserted into this linked list. Okay, so the very first thing, whenever you insert a new node, what you need to do is you need to, okay, so you need to create a memory or allocate memory for the new node. Allocate memory for the new node. Okay, so how you allocate memory for the new node? By creating an object for this class. By creating an object for this class called as a node class. Okay, so that means you call the constructor. Okay, so if you call this constructor, how you can call this node class constructor? Just by specifying the class name. Okay, by specifying the class name, and within the parameters then you pass the data. Okay, so you pass this data. So assume that data value is 10, node 10, you create node 10. What happens means this calls the node class constructor. Okay, so immediately the memory will be allocated like this. Memory will be allocated like this. Then it allocates self dot data is equal to data. Okay, so here the first member is called data and the second member is called next pointer. This is called next pointer. So what it is doing is self dot data is equal data means 10 will be inserted here. Then the next pointer will become none. Okay, so this node address, you should catch somewhere. Okay, so you should store somewhere. Then what I am doing is I am storing in a variable called as a new node. Okay, so that means there is a variable created called as a new node. Okay, and this node is pointing to this object, node object. Okay, so this is the memory, actual memory created for the node. Okay, so this memory address I am storing in the variable called as a new node. Okay, so this is the very first thing you need to, whenever you insert a new node, first allocate memory for the new node. How you can allocate memory for the new node? Just by calling the constructor of node class. Then pass the data. It creates a new node, and that new node address you collect in a variable called as new node. Now new node is created like this. Okay, so if this has to be inserted at the beginning, head should point to this. Yes or no? Head should point to this. Okay, so then what we do is, if you ask, okay, so how you can ask this head pointer? Always you should ask access by using the self parameter, self dot head. Okay, so if you say self dot head, what is the present in head? None is there. Okay, head contains none. Okay, so if you say if self dot head, if none means it becomes false. It becomes a false. Okay, so then to make it as true, what we can do is we can use not here keyword. If not self dot head, the meaning is if self dot head, if head is not pointing to anything, if head is not pointing to anything, okay, so that means head contains none value. Head contains null pointer. If head is not pointing, so you can say please point to this new node. That is what we can say. Okay, so how you can say that? Please point to new node. Then you can say that self dot head is equal to new node. This is how you can write a statement. Okay, so that means new node. What is new node? This is address here. Okay, that address we are assigning to head. Okay, so the same address will come here. Nothing but now you can say that head is also pointing to this. Now, since the same address comes here, head will point to this first node. That means the new node becomes the first node. Okay, so then one more time we'll try to add this function, execute this function, insert at beginning. Okay, so 10 we have inserted now. So next time data value, for example, 20 will take. Now I want to add 20 at the beginning of the list. Okay, so at the beginning of the list I want to add. Okay, so assume that now our list contains only one element. Okay, so that is 10. Okay, now we want to add 20 at the beginning. What we need to do, we need to call this function, insert at beginning function you should call. Okay, so how it executes, what it is doing, the very first thing is it is allocating memory. I'll take different color here. Okay, so you can see here one more element I am adding. So then first it creates the node. Okay, so a new node is created here. Just see here, new node is created. Okay, that means node of data means what happens? It goes to class and it executes this constructor, init function it executes. Okay, so self dot data is equal to data, something like 20 will be stored here. Okay, then self dot next is equal to none, this next will become none here. Okay, then what happens? What happens here? Okay, so this code it is executing. Okay, so after that means the node is created here. That node addresser. Okay, so where we are storing? We are storing in a variable called as a new node. Okay, so it creates a variable called as a new node, and this new node is now pointing to this 20. Okay, now it comes to the next line. If not self dot head, okay, it is just like if head is not pointing to anything, if head is not pointing to anything. Okay, but now you can see how this statement is executed. It says self dot head, self dot head. What is the value? It contains some number. It contains some address. Address is nothing but a number. So all numbers it takes as a true here. Okay, so it takes as a true. So then this becomes true. Not true means it becomes false. Then this if statement is not executed. This if statement is not executed. Okay, so do we require this? Do we require this checking of this? I think this is not required here. Okay, because uh, if it is the first node, okay, so you can directly add the element. Okay, so not required this first checking here. After adding the new node, okay, then you can say self dot head is equal to new node if you say. Okay, now if self dot head is equal to new node, if you have written here, what happens? We'll see here. New node is allocated here. Then you, if you say self dot head is equal to new node, head will point to this new node. Head will point to this new node. Okay, but this new node next pointer should point to previously first node. Okay, 10 is previously first node. Okay, this node address first you should bring here. You should set this pointer first. That's why before this what you need to do is this new node address. Okay, so this new node next pointer, you should make this to point to previously first node. This link you should set first. Okay, so how you can access this one? So you can say that new node dot next, new node dot next equals to, okay, so equals to, okay, so this is the first node, previous first node, where its address is present in head. Okay, so then you should say self dot head. When you say self dot head, first the new node next pointer we are setting here, it points to previous first node. Now you remove this and make the head to point to this node, then it becomes the first node. Okay, that is what we are doing. Head is equal to new node we are saying. Now head points to this node here. That's it. Okay, so no need of checking any condition here, just beginning, no. So directly you can set these two pointers. That's it. Element will be added at the beginning. Got it? Any doubts in this? Right. Next. So this is a inserting element at the beginning. Okay, so we'll take a new list and we'll try to add element at the end of the list. Okay, so I just erase everything. I create a new linked list. Then we'll write a function here. Okay, so we'll go to the next slide. Okay, it is in continuation. Okay, so here I'll show. So what we do is we create a linked list. Assume that we have linked list with three elements, 20, then say 30. This is none. Okay, so head is pointing here, pointing to the first node. Okay, now we want to add element at the end of the list. Okay, so new element 40 we want to add at the end of the list. Okay, so for that again you need to define a function called as a insert at end. Insert at end. Okay, so for this the first argument is self, the second argument should be data. Second argument should be data. So what we need to do, if you want to create a new node, what I said, first thing is you allocate memory for the new node, allocate memory for the new node. Okay, so then store this data and this becomes a none. This is all done automatically if you call the constructor of a node class. Okay, so how you can allocate a new node here, just call the constructor node and pass this data. Okay, so this diagram is created with this statement, and that node address you store in a variable called as a new node. Okay, so then a pointer called as a new node will be created pointing to this new node. Okay, right, so new node is a created, but this node has to be added at the end of the linked list. Yes or no? This new node has to be added at the end of the linked list. Okay, so assume that if initially you can add element by using insert at beginning function or insert at end function also. Okay, so I am just taking an example. If initially if your head is none, head is none here. Okay, that means your linked list is empty, and if you want to add a new node at the end, that becomes the first element itself. The new element becomes the first element itself. This condition you should check first. If the linked list is a empty linked list, okay, even though you add a list new element at the end, that becomes the first node. Okay, so how do we know this? Now here we should use that function. Okay, so if condition, if not self dot head. Okay, so self dot head is none here. Okay, that means if head is not pointing to anything, then we'll say please point to new node. Okay, so we'll simply say that self dot head is equal to new node. Self dot head is equal to new node. So what happens? This head now points to this new node. It points to the new node. That becomes the first node. Okay, so after adding this, just you say return. Come out from the function. This it checks if it is empty. Okay, so initially if the list is empty, okay, so if the list is empty, then it executes this code. It executes this code. Okay, so we assume that there are some elements in the list. What we need to do, we will see here. Okay, so assume that our list contains 3 elements and 40 we want to add as a fourth element into the list at the end. Okay, so now what we do is we'll try to add this at the end of the list. Okay, so in such case what we required, if this is the last node, then 30 should become its previous node. Okay, so this 30 node address you should acquire. You should get this 30 node address. Okay, that means what you need to do, you need to traverse the list until you reach the last node. Okay, so here you should traverse the list. You should visit each node and go to the last node. You should go to the last node. Okay, so how you can go to the last node? By using a temporary pointer. Okay, so you should use a temporary pointer. Okay, so you can use a pointer called as temp, or you can use a pointer called as a current node, because always current node points to something like current node. Okay, so we'll say that the current node, okay, so is equal to self dot head. You should always start from the first node only. You should always start from the first node only. You should not disturb this head pointer. Okay, so what we do is we take a temporary pointer called as a current node. Okay, so this we call it as a current node, and this current node points to the first node. Okay, so where is this 30? You do not know. Where is the last node? You do not know. Okay, so that means how do we know that we have reached the last node? That is the point here. While traversing, where we should stop? How do we know that we have reached the last node? Okay, so we can understand that you reached the last node if the node's next pointer is null. If the node's next pointer, the point whose pointer is none, then that indicates the last node. Yes or no? Okay, so the last node's next pointer contains none. Until you reach the last node's next pointer as none, you should traverse the list. Okay, so when you get this, then you stop here, then you'll get the last node address here. Okay, so for that you need to traverse the list. For that you should use a loop here, while loop. Okay, so while, okay, while, now you can say current node. Okay, so current node dot next pointer. Okay, so as long as, okay, current node dot next not equals to none, not equals to none. Okay, that indicates that there is one more node. There is one more node. Okay, so then go to the next node. Now you say current node is equal to current node dot next. Current node dot next. That means we are asking the current node to go to the next node. That is the meaning here. Okay, so while current node dot next not equals to null. Okay, now see what happens, how we can reach 30 node. Let us execute this code. Current node is this first node. Okay, so it checks while current node dot next. Current node dot next means this one is not equals to none. Yes, there is some address. Address indicates that it is not equals to none. True. Then we say that current node is called current node dot next. Current node dot next means what it indicates? This node address. That node address we are storing here. That means what we are doing is we are making this current node pointer. We are making this current node pointer to point to the next node. Now it points to this node. It points to this node. Okay, this node address we are storing here. Again it goes up while current node dot next not equals to none. current node dot next means this one. Not equals to none, yes, because this node address is there. Okay, so true. Then we say that current node is called current node dot next. That means it goes to the next node. It goes to the next node. It points to the next node. Again, it goes up. Current node dot next not equals to none. Now see here. This is current node dot next means this one. Not equals to none, false, because here it is none. So false. That means the loop terminates here. When the loop terminates, now you can see current node pointing to the last node. That means we obtained the last node address. We obtained the last node address. We are at the last node. That is the meaning there. Okay. So once you reach the last node, okay, so what you can do is just you manipulate 2 pointers. That's it. Okay. So 1 or 2 pointers, if you manipulate, that is enough. Now once you are at the last node, this node address, once you know what you need to do. Okay, if 40 should be the last node, this node address should present in 30. Okay, so that means this node address you should store here. Here you should store that 40 node address you should store here. Okay, how we can store that we will see here. So I just remove here, instead of none here, what we can do is we make this pointer to point to this node. Okay, so how we can do this, what is this node? This node is called new node. Okay, so after coming out from the list, okay, so we'll say that new node address we want to store. Okay, so this new node, where we will store? Here. How to access this location? It is current node dot, this is next field. Okay, so you should say that current node dot next, current node. Okay, so dot next, current node dot next is equal to new node. When you say, so then the last node pointer will point to this. Then anyhow this is the last node, no, so this is none already created. Okay, so just by changing one pointer here, you are able to add element at the end. That's it. This is your code. Insert at end. Okay, so this is the code for insert at beginning. Now you can add in a linked list either at the beginning of the list or at the end of the list. Got it? Okay, so then we'll write a function for displaying the elements in the linked list. That means we traverse the list. Okay, so once you get that, we can execute this piece of code and we can see whether the function's working fine or not. Okay, so for that we write a function. Okay, so you can call that function as a traverse or display. You want to just display the elements of the linked list from left to right. Okay, so we just call it as a traverse. Okay, assume you have a linked list like this, 10, 20, okay, then 30, this is initially, assume that you have created a linked list like this. Now we want to display the elements of the linked list. What we do, we define a function here, define traverse or display, whatever name you want, you can use, and there will be only one argument called as a self. Okay, so this prints the data present in all the nodes in the linked list. Okay, so if your linked list is empty, if your linked list is empty, that means no elements are there, you cannot traverse the list. Okay, so that you should handle first. How do we know that our linked list is empty? If a head pointer contains none, if our head contains none, then you can say that linked list is empty. That first you should check here. Okay, so if how do we know that? If not self dot head, if not self dot head, okay, list is empty. This is good way of writing the code. Okay, you can also write like this, you can also write like this. Okay, You can also write like this. If self dot head, generally this is a elementary way of checking the code. If self dot head is equals to none, okay, so then what we can do, we can just say print, okay, so linked list is empty, okay. You cannot print the elements in the linked list, then you can say return, directly you come out from the program. Okay, so instead of writing like this, okay, so self dot head is equals to none, checking a condition, okay, so you always write a better code. So that is, anyhow, self dot head is false, okay, so then say not self dot head, okay, so this seems to be better way of writing the code. If not self dot head, the meaning is if head is not pointing to anything, then we'll print the linked list is empty, return. Otherwise what you need to do, you need to traverse this list and print each node by using a temporary pointer. Okay, always you should use a temporary pointer that we called as a current node. Okay, so we create a variable called as a current node. Okay, and you start from the first node address is where it is present in a head. Okay, so that's why we create a variable called as a current node. Okay, so this is equals to self dot head. This is equal to self dot head. Current node is equal to self dot head. Okay, so you can ask here, for head we are using self dot head, you are saying sir, but for current node you are not using self. Okay, so since this head is a class variable here. Okay, so the head is a class variable here. Just see here, it is a class variable. Okay, so the class variables must be accessed using the current object. Instance variables must be accessed using the object. Okay, so that's why these instance variables here, for node also these are instance variables. Okay, so they must be accessed using the current object. Here the current object is self. Okay, so but whereas this new node and current node, they are variables of this function. Okay, so that's why it is just a variable defined inside the function, local variable. It is a local variable of this function. Okay, so that's why it is not required here, self is not required. Okay, so this differentiation you should understand. So current node is equal to head. Now current node is pointing to the first node. Okay, so then you want to just print some message on the screen, just you print here. Okay, so just you can write here the elements or something, you can write the elements of linked list. Some heading you can print, you can go on printing the values here. Okay, so the elements of linked list you can just print here. Then what you need to do, you should traverse the link up to end of the list. How do we know that you have reached end of the list? I said that if last node, that means the current node next. Okay, so it is not equals to none or it becomes equals to none, that means you reached the last node. Okay, so that means you should traverse the list now. So while, you can write like this, while current node. Okay, so while current node dot next means you should stop at last node, or last node also you should print the last node also. Okay, so that's why you should check here, while the current node, okay, so not equals to none, while the current node not equals to none. Okay, so what it does, now see, current node not equals to none, there is some address means none, not none, not equals to none, true. Okay, so now you print it, that means current node is pointing to some node, you print its data. Okay, so how you can print its data, Just you can say that print. Okay, so print this value 10. How you can access this value? You can just say that current node dot data, current node dot data. Okay, so then comma, we will print the data like this on the screen, 10 followed by some arrow mark, then 20 followed by some arrow mark. In this way we will print. So current node dot data means it prints 10 here. Then after that you want a arrow, no? So in use attribute called as end. In end you use this arrow. So then it prints arrow after printing a 10 value like this. Okay, so once the first node is printed, now you make the current node to go to the next node. Okay, so just move the current node to the next node. How you can move? Now you can say current node dot next is equals to, sorry, current node equals to current node dot next. Current node is equals to current node dot next. Current node dot next. That means go to next. That is what we are informing. Okay. So current dot next means this address. This address present here means now you can say that this is pointing to the next node. It is pointing to the next node. Okay. So again the loop repeats. Okay. So it goes up. It checks here. While current node not equals to none. So this 20 node address is present in. Some address is present. Not equals to none. Yes, true. Then again it prints current node dot data. Current node dot data means it prints 20 here. Okay, so 20 will be printed with arrow. Okay, so then current node is equal to current node dot next you say. So that means this moves to the next node. It goes to the next node. Then again goes up. Current node not equals to none. Yes, 30 address is present, not equals to none. Then it prints current node dot data. That means it prints 30 followed by arrow. Okay, so then current node is called current node dot next. Now see here, current node dot next means what is there here? None. Okay, so that means now the current node contains none. Okay, so that means this is deleted. Now it contains a none value here. Okay, so now your variable current node contains a none here. So when it goes up, it checks current node not equals to none, false, because there is none in this. Okay, so that indicates that you have traversed the entire list. Like this it has printed. Once you come out from the loop, what we do is we'll print a variable, because there are no more elements at the end. We'll print a none here. Okay, so just I print here, I print a message after the arrow none. So it seems that it none will be printed at the end. That's it. This is the function for traversing the list. Got it? Now when you print, the elements will be printed in this order. Okay, so which confirms that your functions adding at the beginning, adding at the end are working fine. So shall we execute this code? Shall we execute this code? Now let me open online compiler. I'll open the online compiler. Okay, so then I'll execute this code. So yeah, this is the compiler. Right, so quickly I'll type the code. Just we will execute the code. Okay, so then what else we require? Functions we need to write now. Okay, so insert at beginning and insert at end. Got it? Right. Now, once you define the two classes, okay, so the main function, how to write the main function, that we missed here. Okay, so let us see, this is the node class we defined here. Okay, then linked list class we defined. This is only class definition. Okay, so how to write the main code here? Now the main code should be written like this. Okay, so in the main code, what you need to do, first thing is you need to create an object for the linked list class. Okay, so that means how do we create a object for the linked list class? By just calling the constructor here. Okay, so just you say linked list. Okay, so then call it as a L list. Call it as a L list. Now we can say that the linked list object is created. Okay, so an empty linked list object is created. So L list will point to an empty linked list object. Okay, the init function. Okay, so what it does here, it creates inside the L list. What it does, it creates a head pointer initially pointing to none. Like this, the empty linked list is created. Okay, so then what we need to do? Now we need to insert elements at the end and at the beginning by using the functions. Okay, so what we do is we call the functions first. L list, because the list is empty, no? So we can say L list dot inserted beginning. Okay, so inside the class, methods must be called by using object. Now this is our object created, L list dot. Okay, so insert at beginning. This is our function name. Insert at beginning. Then you'll set data value. You pass the data 10. 10 will be inserted. Similarly, you can say list dot insert at end. Insert at end. Okay, so then something like 20 I add. 20 will be added at the end. Okay, so similarly you can add something like again one more element. So what it does, it creates a linked list like this. 10 is added at the beginning. Okay, then 20 is added at the end, like this. It creates the linked list in this fashion. Okay, so if you add one more element at the end, so one more element will be added at the end. Insert at end 30. Okay, so one more element 30 will be added at the end. Like this, the list is created. Okay, so once the list is created, then what we can do is we can traverse the list. We want to print the list. Okay, so how we can print the list? By using the traverse method. Now you call the traverse method, list dot l list dot traverse. Just you call the method. Now this becomes your main code. Okay, so this is the main code or driver code, you can say. Okay, so now your code executes. Okay, and whether it is performing the operations correctly or not, we can see by printing the list. Okay, so this thing we will do in our uh, online compiler. Okay, so we'll copy and we'll try to print the list. The code we will copy. Okay, then we'll try to execute this code. Okay, so you can see here. Let me open the online compiler. Now you can observe here. Okay, so I have created a class called as node. So these indentations missing here. Okay, this creates problems. Right. Okay, so head is the start of the list. Initially, it contains a empty. Okay, so it points to the first node. Initially, the list is empty now. Okay, right. So node class I have defined here. Then I have defined the class called as a linked list containing the init method. Then traverse method I have defined here. Okay, right. Then this is the traverse method. Then I defined a insert at beginning method. Okay, so then I defined a insert at a end method. Okay, now this is our main code. Now I am creating an object for the linked list class. Then I am calling this insert at end 10, then insert at beginning. In any order you can call these functions. Okay, then insert at end 20. Okay, then I am traversing the list. Now if I run the code, let us see what happens. Okay, so list traversal, it prints just like a list traversal. I have uh, written here list traversal. Okay, so 5, 10, 20, this is how it is printed. If I remove this end here, okay, so then I can change the name here. Instead of list traversal, I can say the elements of a linked list. Okay, so now you can see the elements of linked list. The list is printed in the next line. 5, 10, 20, then none. Now you can see here in which order we call the functions. Now first insert at end. 10 will be added first. Then insert at beginning. 5. 5 will be added before 10. 5 is added before 10. Okay. Then again insert at end 20. 20 is added at the end. That means after 10 it is added at the end 20. Okay. So that's it. So this way we can perform insert operations on the linked list. We can create the linked list. Okay, then we can add elements at the beginning, at the end, or at some required position. Okay, after some element. For example, you want to add a new element after 10. Okay, that means in between 10 and 20 you want to add a new element. Okay, so those operations we will discuss in our next video. Okay, and also deletion of a particular element from the linked list. These operations we will discuss in our next video. If you have any doubts, please type in the chat. So this is the same. See, so writing of a code, each line you should generate on paper. Okay, so this you should practice. Once you get that ease in writing a code, okay, then any complex given any complex problem, you can write the code easily. Just typing and executing takes hardly 5 to 10 minutes, but generating the code on paper requires the actual logic implementation. You really understand what is happening, how the list is created, how where the element is inserted in the linked list. These things clearly you should understand. So if you found this video useful, please like and share this video, and also subscribe to my channel if you are new to the channel, and also turn on the bell icon for more such programming updates and programming tips. So thank you one and all. Happy learning, happy coding.